This is lecture video 55, and we will cover limit comparison test in this lecture. Okay, this is another test that will help us to understand whether given an improper integral is convergent or divergent. So limit comparison test is stated like this. You want to understand whether this improper integral of type 1 is convergent or divergent. Then you will use another function g of x to understand its behavior, and you will look at this limit of their quotients, of their ratio. So if this limit is a limit between 0 and infinity, then the conclusion is they both converge or they both diverge. Okay, so let me emphasize that this is an improper integral of type 1. And here we have a remark saying that the limit comparison test, which is stated here for the improper integrals of type 1, this result is also valid for the improper integrals of type 2 as well. Okay, let's try to apply this test in this example. We want to investigate the convergence of this improper integral of type 1. So you remember we also covered direct comparison tests to use for such questions. Let's first try to use direct comparison test and see why it does not work here. Okay, you can compare this quotient with this one, right? As the denominator here is less than denominator 1 on the right, obviously the left-hand side will be less than or smaller than the right-hand side. Then, if you investigate the convergency divergence behavior of the right-hand side, it won't take too long because this is a p-type of improper integral where p equals 1. That's why by using the p-test, it diverges by p-test. So how do you conclude here? So the integral with the bigger terms diverges. So the integral with the smaller function, smaller function now may behave like convergent, finite, or may behave like divergent because, you know, its upper bound is infinite and the smaller thing can be either finite or infinite. You cannot decide this. That's why direct comparison is not working here. The direct comparison test does not work here. So this may converge or may diverge. You cannot make sure of it. So direct comparison test fails for this question. Fails, and for such situations, you can fill this gap that is that remains after applying direct comparison test. You cannot give the result. There is a gap. There is still this gap. You can fill this gap by using limit comparison test. So let's try limit comparison test instead. Okay, our function f of x is this one here, 1 minus e to the power minus x over x. And to be able to use this test, limit comparison test, you need to choose a function gx. How to choose it? You will choose, okay, so we can choose 1 over x as our g of x here. Okay, so let's apply limit comparison test. I will take the ratio like that and look at the limit as x goes to infinity. Limit as x goes to infinity, f of x over g of x. I want to compute this limit. So what I have minus x over 1 over x. That's why you will simplify this. And then what you have here is as x goes to infinity, 1 minus e to the power minus x. So limit as x goes to infinity, 1 minus 1 over x. So what happens to this expression as x goes to infinity? It goes to 0. That's why the result of the limit is 1. So you see we obtain a limit L between 0 and infinity, just like written in the statement, then we can use the conclusion. Then the conclusion is these two improper integrals of type 1, they either both converge or both diverge. So what is the behavior of our g of x? We already expressed here that it is divergent by p-test, remember? So let me write that down also here. So the conclusion is they both converge or both diverge by limit comparison test. So let's look at g of x dx. Is it convergent or divergent? As p equals 1, it diverges by p-test, as we indicated above. So the function f of x will also diverge by using limit comparison test, because we obtain a limit between 0 and infinity, and this means that they both converge or both diverge. 1 to infinity f of x dx, which is 1 to infinity, which is our original question, also diverges by which test? By limit comparison test, okay? So from this line to the last line, we use the conclusion of limit comparison test, okay? So they both converge or both diverge. Let's look at the next example. Here, investigate the convergence of this complicated function. So our function f of x is given as x over x to the power 5 over 2 plus 1 times x to the power 1 over 3 plus x to the power minus 1 over 3. Now we want to apply limit comparison test here. To be able to apply it, we need to choose some g of x function, right? Now, in the previous question, I didn't tell you exactly how to choose this g of x function, because we had a candidate after analyzing the direct comparison test that we choose this candidate as our g of x. But here, I will tell you some certain way about how to choose your g of x function. You will choose the dominating terms in your function. Okay. Choose the dominating terms. This will be the way of choosing g of x. So x in the denominator will stay as x because there is no other term. But look at the denominator. In the denominator, the dominating term is what? It is the term that you have the highest degree for x. So it is x to the power 5 over 2 times x to the power 1/3. So this will be, after you do this multiplication, this will be the dominating term for the denominator, right? Okay, then your g of x function becomes x to the power 5 over 2 plus 1 over 3 minus 1 because of this denominator. So it is in fact 1 over x to the power 11 over 6, right? After you compute the power, it is 11 over 6. So this is your g of x to be used in the limit comparison test. So now I am applying limit comparison test with the g of x that I find by choosing the dominating terms. So let's compute the limit with this g of x. Okay, I am computing the limit now. It is f of x over g of x as x goes to infinity. Okay, x goes to infinity, I have f like that. X over 5 over 2 plus 1, 1 over 3 plus minus 1 over 3. Okay, in the denominator, I have this 1 over x to the power 11 over 6. So the result of this limit will be 1. How do I know it? Because the highest degree terms for the numerator and the denominator are equal because of the way that I choose g of x here. So I look at the dominating terms, highest degree terms, just choose them for g of x, so it will be the same here for the numerator and denominator, and the ratio of the coefficients of the highest degree terms, which are 1, 1, will give you 1 as a result of the limit. So here you obtain a limit between 0 and infinity. So this fits to the structure here. That's why you can use the conclusion of the limit comparison test now, which is they both converge or both diverge. Okay, so if g of x converge, f of x will converge too. If g of x diverge, f of x will diverge too. That's why we need to understand the behavior of g of x. So from 1 to infinity, x to the power 11/6. So this is a p-type integral where p is 11/6, which is bigger than 1, so it converges. That's why by using limit comparison test, the integral with f of x from 1 to infinity. Okay, let me write the function quickly here. 5/2 plus 1/3 plus x to the power minus 1/3. Also, it has to be convergent because of the result that we find for g of x. It converges as we obtain limit 1 in limit comparison test. They have to both be convergent. That's why f of x should also be convergent, okay? So let's look at this one. And let's try to understand what to do. 1 plus sine x over x squared. Maybe, okay. So you can solve this one by using direct comparison test. That's why I want to move to the next example. Okay, let's deal with this one. Limit comparison test we will apply. So how do we apply it? You look at your f of x function, and by choosing the dominating terms, you decide what should be g of x. Okay, 1 is 1 obviously, and which one is bigger at the denominator? Obviously, e to the power x is bigger than 2 to the power x because e is a number 2.6 or something. So I choose e to the power x as it is the dominating term for the denominator. This is our g of x. And I start computing the limit now with this g of x function. Okay, let's compute the limit. X goes to infinity. What we have here, we have 1 over e to the power x, 2 to the power x, and we have 1 over e to the power x here. So let's rewrite it as x goes to infinity, e to the power x minus 2 to the power x. And this can be rewritten as, if you want exact computation, let's do it. 1 minus 2 over e to the power x like this, and these are cancelled. 2 to the power 2 over a is something less than 1. So if you have a real number less than 1, and if you send its power to infinity, you obtain what? Okay, so 2 to the power is 2 over e is something less than 1, and 2 over e to the infinite goes to 0 then, right? Because every time you increase the power, the value of this rational number will get smaller. That's why this part goes to 0 as x goes to infinity. So the result of the limit is 1. Okay? 1. So you obtain again some limit L between 0 and infinity, which shows by the limit comparison test that they both converge or both diverge. Both converge or both diverge. That's why I will investigate the behavior of g of x function. So Is it a convergent one or divergent one? Let's find out. Okay, this is e to the power minus x dx, and you can evaluate this improper integral by using the standard computation. You know, just put b here and then put b goes to infinity here. So the result of this integral is minus e to the power minus x from 1 to b, like that. So the result is limit b goes to infinity minus 1 over e to the power b minus 1 over e, right? Like that. Okay, so as b goes to infinity, this part goes to 0. So the result is 1 over e, which is a finite number. That's why. So this improper integral is convergent, converges. Okay, so this shows that this improper integral converges. That's why by using limit comparison test, the original improper integral that we deal with, which is with f of x, 1 over e to the power x to x dx from 1 to infinity, also converges by using limit comparison test, okay? If for g of x, the result is convergent, for f of x, it has to be also convergent too, because if you obtain a limit between 0 and infinity, they both converge or they both diverge. Okay, as the last example, we can solve this one, which looks very similar to previous example. We can quickly handle that. So what is our f of x here? It is this one. And we want to apply a limit comparison test. That's why we need to choose some g of x by using the dominating terms. By choosing the dominating terms. So 1 over, obviously the dominating term for the denominator is square root of e to the power x. Okay, so let's start computing the limit now. F of x over g of x as x goes to infinity. Okay, what is it? X goes to infinity. 1 over, okay, let me just write down one step later. So it is in fact like that, square root of e to the power x over this. Okay, what do we have? It is e to the power x, e to the power x parenthesis 1 over like that. Inside the square root, you have this. So these two gone. This is normally infinity over infinity. Okay, let's handle it here. You can apply L'Hopital's rule to see the result of the limit as quick as possible. So e to the power x is e to the power x. So the result of this part as x goes to infinity is 0. That's why the overall limit for this operation is 1. So we obtain what? We obtain a limit between 0 and infinity by using limit comparison test. F and G, they both converge or both diverge. Or both diverge. So let's try to understand the behavior of g of x function. So 1 to infinity, g of x dx. 1 to infinity, 1 over e to the power x square root, okay, dx. So this is from 1 to infinity, e to the power minus x over 2 dx. And you can easily compute it as by using the standard way, like putting b here, sending b to infinity for the result of this integral. Okay, so what do we have? b goes to infinity, what is the result of this interval? It is, in fact, minus 2e to the power minus like that. And you need to insert these upper-lower bounds. Okay, then what we have? We have limit b goes to infinity, minus 2e to the power minus b over 2 minus plus 2 times e to the power minus 1/2. So what we have, instead of writing this, you can take these to the denominator. So it is b over 2 and 1 over e to the power 1 over 2. So as b goes to infinity, 1 over infinite is 0. That's why this part goes to 0. And the result of this limit is 2 times 1 over square root of e, which is a finite result. As this result is finite, this improper integral is a convergent one. It converts. That's why then I can comment on the improper integral with f of x. Remember, we applied limit comparison test by using this g of x. We computed the limit, find the limit between 0 and infinity, meaning that they both converge or diverge. And then we understand that this g of x function is convergent. That's why f of x, which is the original question, should also be convergent by using limit comparison test. Also converges by limit comparison test, okay? That's the result. And that's how you apply limit comparison tests to understand whether the given improper integral converges or diverges. So that's all for this video.